In this video, I'm going to describe to you in detail what OPC UA PubSub is and how it works. And in the last section of this video, I'm going to show you a practical demonstration of how to build an OPC UA PubSub application to transmit OPC UA data over MQTT using NodeJS. A quick thank you to our sponsors. This video is made possible by our friends at HiveMQ, who are providers of an enterprise-grade edge and cloud-based MQTT broker. So please do check them out to help support this channel. My name is Kutsai Manditereza with Industry40.tv, and I regularly publish industrial Internet of Things tutorials on this channel. So if you're new here, please do subscribe and click on the notification bell to make sure that you never miss any of the videos. So in previous videos of this series, I have described to you OPC UA features that are centered around a client-server or request-response model of communication. This is whereby an OPC UA server exposes information about an underlying device, machine, or process. And when an OPC UA client intends to retrieve or update that information, it does so by sending a browse, read, write, or method call service request, to which the server responds accordingly. Essentially, there is this direct and synchronous communication between an OPC UA client and server. And that model of communication works fine in closed-loop, command and control kinds of industrial automation scenarios, where the total number of connections is not very high. However, in the context of industrial Internet of Things, where you are integrating data from many components across operational technology and information technology domains through a centralized platform such as the cloud, the OPC UA client-server communication approach falls short of what is expected. Mainly because, as the number of connected components increases rapidly in industrial IoT scenarios, the OPC UA client-server communication model cannot scale to meet such connectivity demands. Also, using an OPC UA client-server communication approach makes it difficult for smart devices and cloud-based analytic systems that know nothing about the OPC UA platform to gather data from production components that talk OPC UA. So it is with this set of challenges in mind that the OPC Foundation went back to the drawing board to come up with a solution. As a result, an extension to the OPC UA specification was published. This extension is called the OPC UA PubSub specification, which is part 14 of the OPC UA specification. Now, before I go on to describe what OPC UA PubSub is and how it works, it's important that I clarify an issue that might cause some confusion. And that is, the client-server model of communication in OPC UA has an inbuilt subscription feature that is used for monitoring changes in the OPC UA server. However, this is a totally different kind of subscription mechanism that needs not be confused with the Part 14 PubSub specification. Firstly, in the original OPC UA client server publish subscribe feature, each OPC UA client creates for itself a single or multiple subscriptions to an OPC UA server. For example, a subscription could be a monitored item subscription, whereby an OPC UA client requests an OPC UA server to monitor a certain variable, and when a change is detected in the value of that variable data is pushed to the OPC UA client. And it could be an event notifier subscription, whereby an OPC UA client requests an OPC UA server to watch out for a certain event, and when that event occurs, the server sends an event notification to the client. However, the underlying fact here is that these subscription interactions require the creation of an individual session for each OPC UA client and server, which makes it strictly an OPC UA client-server communication. So whenever I mention PubSub in this video, I'm referring to the Part 14 PubSub specification and not the inbuilt subscribe feature of the OPC UA client-server communication. Now that we've got that out of the way, let us understand what OPC UA PubSub is and how it works. OPC UA PubSub rides on top of a pattern of communication that is popular with IoT systems. This is whereby, instead of establishing a direct line of communication between the sender and receiver, an independent communication system is used to manage the communication on behalf of both the sender and receiver. In other words, instead of being asked for data by separate OPC UA clients individually, an OPC UA server can push data values to a group of data consumers who have expressed interest in that data stream by subscribing to it via an intermediary communication system. Hence, the much desired one-to-many and many-to-one industrial IoT communication can be realized easily and with extremely low resource consumption on the sender side, as it would be no longer the task of the sender to communicate with all participants one by one. Simply put, OPC UA PubSub is an extension to OPC UA that enables communication between system components using a publish-subscribe pattern instead of the request-response pattern. Now, the device or system that sends the OPC UA information to an intermediary communication system for consumption by other systems is called a publisher in general or an OPC UA publisher in particular. And the systems that receive this information are called subscribers. And due to the decoupled nature of the publish-subscribe communication pattern, the number of subscribers receiving data from a publisher does not influence how the publisher produces the data. And as it turns out, most cloud platforms use a publish-subscribe communication pattern for managing device-to-cloud and cloud-to-device messages. So the OPC UA PubSub model of communication makes it possible for OPC UA devices and applications to transmit plan flow data directly to data services hosted in the cloud for analytics. Now, it's important to mention here that when we talk about OPC UA PubSub, we're not talking about an OPC UA client gateway that collects data from an OPC UA server and publishes it to the cloud. Rather, we're talking about an OPC UA server that implements PubSub functionality and publishes information directly from itself to the cloud. Okay, now that we understand the principles on which OPC UA PubSub is built, let us look at how the OPC UA PubSub communication really works. So, like other OPC UA specifications, OPC UA PubSub is an abstract specification, meaning that it is not bound to a particular messaging system, although it does provide specification for communication parameters and transport protocol mapping. And because of this abstract definition, OPC UA PubSub can be used to transport different types of information through different types of networks. For example, OPC UA PubSub can transmit binary encoded messages over UDP, and it can also transmit JSON encoded messages using protocols such as MQTT and AMQP. Now, as already highlighted, in OPC UA PubSub, the participating OPC UA applications can assume the roles publisher and subscriber. Publishers are the sources of data, while subscribers consume that data. Contrary to a service-oriented communication approach used in OPC UA client-server model, whereby participants communicate by providing services to each other, OPC UA PubSub model uses a message-oriented approach whereby participants communicate by exchanging messages. Again, publishers send messages to a message-oriented middleware without knowledge of what components are subscribed to receive the messages from the middleware. Similarly, subscribers express interest in specific types of data without knowledge of the publishers pushing this data to the message-oriented middleware. And the message-oriented middleware itself can be a software or hardware infrastructure that coordinates the sending and receiving of messages between publishers and subscribers. Now, here's the important part. The OPC UA PubSub specification does not define a message-oriented middleware. What the OPC UA PubSub specification does is that it describes two types of message-oriented middleware that it supports: brokerless middleware and broker-based middleware. In brokerless form, OPC UA PubSub relies on the network infrastructure to deliver messages to one or more receivers, meaning the message-oriented middleware is the network infrastructure itself, things like network routers, switches, or bridges. Further, in brokerless form, publishers and subscribers use datagram protocols like UDP or UADP, which is a combination of UDP multicast and UA binary encoding. In other words, even though a one-to-many message distribution is achieved, it is not through a third-party message broker. It is achieved through multicasting of UA binary encoded OPC UA publisher messages using UDP. And the advantages of this model include that it only requires standard network equipment and no additional software components like a broker. Message delivery is assumed to be direct, without software intermediaries and therefore provides reduced latency and overhead. On the other hand, in broker-based form, the primary component of the message-oriented middleware is a message broker. In this case, no application is speaking directly to other applications. All the communication is passed through the broker, and then the broker routes the messages to the right applications based on business criteria. In broker-based form, subscribers and publishers use standard messaging protocols like MQTT or AMQP to communicate with the broker. In other words, a third-party server or message broker is used for distributing JSON-encoded publisher messages to receivers who have subscribed to receive this information. The message broker can reside in the cloud or anywhere where it is visible to both the OPC UA publisher and the subscribers. The advantages of this model include that the publisher and subscriber do not have to be directly addressable. They can be anywhere as long as they have access to the broker. Secondly, this fan-out architecture allows a very large list of subscribers, multiple networks, or even chained brokers. Now, it goes without saying that your choice of communication protocol depends on your application. But to make it clearer, let me highlight a few possible use cases for both brokerless and broker-based approaches. So, a broker-based OPC UA PubSub approach using MQTT or AMQP would be more suitable for industrial Internet of Things applications where there is a large number of receivers, hundreds or even thousands, that are subscribed to receive a stream of information from a message broker that would typically be located in the cloud. On the other hand, a brokerless OPC UA PubSub approach using UADP or in the future Ethernet APL is best suited for controller-to-controller communication or in scenarios where there is a frequent exchange of data, such as in a production environment or robot control. And by the way, OPC UA PubSub does not require for publishers and subscribers to be either an OPC UA server or an OPC UA client to participate in PubSub communications. Okay, now that we understand the basics of how OPC UA PubSub works, I would like for us to dive deeper to understand how it actually works under the hood, highlighting the entire process from the time processed data is prepared for publishing in the publisher up to when it is received and processed in the subscriber. In OPC UA PubSub, the publisher is an entity that sends network messages to a message-oriented middleware. The publisher represents a certain information source, which could be a control device, a machine, or a manufacturing process. In most cases, although not required, a publisher is also an OPC UA server. The first step in the OPC UA PubSub process is the creation of a PubSub connection. This is where transport protocol specific parameters may be defined for the PubSub connection. For example, MQTT protocol and the respective broker URL address. The next step is the collection of data that needs to be published from the server's address space. This data that needs to be collected is called a dataset, and the collection of a dataset is achieved through what is called a dataset collector, which pulls a dataset out of the OPC UA server's address space as per configuration. A dataset in this case can be thought of as a list of name and value pairs representing a list of variable values or events. Now, when this dataset is collected from an OPC UA server, it needs to be put inside a container for publishing. That container of information to publish is called a published dataset. And because when this published information reaches a subscriber, it will need to be decoded accordingly, the published dataset needs to define and include what is called a dataset metadata, whose job is to describe the contents and semantics of that dataset so as to help a subscriber interpret the published information the same way as the publisher. Next, a publisher component called a dataset writer takes the dataset and creates what is called a dataset message. And for structuring a dataset message accordingly, the dataset writer refers to the dataset metadata, which defines the fields to be contained in the dataset message. The order of the fields in the dataset metadata is made to match the order of values in the published dataset messages. Additionally, the dataset message would include a dataset writer ID, which is meant to identify the dataset writer. Each dataset is sent as a separate dataset message, serialized with a format that depends on the dataset writer. One dataset message format is the JSON message mapping, which represents the dataset in a format which subscribers can understand without knowledge of OPC UA. Another dataset message format is the UADP message mapping. However, a dataset writer which is linked to an existing published dataset needs to be contained within what is called a writer group. Each writer group can have one or more dataset writers, and it contains information that makes it possible to combine dataset messages from different dataset writers to form what is called a network message. A network message is the actual message that is finally handed off for delivery to a specific message-oriented middleware using a specific transport protocol, which could be MQTT, AMQP, or UDP. The network message uses data that is provided by the dataset messages to form a payload and attach to it a publisher ID to identify the publisher of this information in the network. Before we move on, it's important to mention here that even though the process is the same, not all OPC UA publishers implement components like dataset collectors and dataset writers as independent entities. So it's best to consider this as abstract. Now, on the receiving end, before any network message can be received, the subscriber needs to establish a connection to the required message-oriented middleware. And to determine which message-oriented middleware to subscribe to and for which dataset messages, a subscriber can be pre-configured with the URL address of the message broker. Now, as highlighted earlier, an OPC UA PubSub message carries with it the dataset metadata, which can provide important additional context that allows the subscribers to properly interpret the message. So what that means is that once a network message has been received, it is decrypted and decoded, and each dataset message is passed on to what is called a dataset reader. The dataset readers, which have settings that enable them to filter the received network messages and dataset message, are grouped into what is called a reader group. The dataset reader then uses the dataset metadata contained in a subscribed dataset for decoding the values of a dataset message to a dataset. And then the decoded information is pushed into the subscriber application, and if the subscriber is an OPC UA server, the received values are then mapped to nodes in the subscriber's address space. Okay, so we've gone through how OPC UA PubSub works, and one big takeaway here is that OPC UA PubSub is a generic communication mechanism that is designed to work over any message-based middleware. What I would like us to do next is to look at one implementation of OPC UA PubSub, which is OPC UA over MQTT. Simply stated, OPC UA over MQTT is a mapping of OPC UA PubSub features to MQTT features. OPC UA over MQTT uses a standard configuration tool to map elements defined in the PubSub specification, such as publisher IDs and dataset writers, to an MQTT topic tree in a way that follows an OPC UA recommended MQTT topic structure. The configuration information can be uploaded or downloaded from devices and machines in the form of a compact file that follows a standard OPC UA PubSub configuration information model, meaning that you can use a configuration tool developed by one vendor to remotely perform MQTT topic structure configuration on a machine built by a different vendor. Here is what the recommended OPC UA over MQTT topic tree looks like. It consists of a prefix, encoding, and message type, which are the primary elements of the topic tree. The prefix is system defined, and it provides a scope for the publisher IDs. Encoding specifies the format of messages in the topic, and the message type specifies the content of the messages published by the subtopics. And then these primary elements are followed by the configurable elements that form a hierarchy. These are published ID, which represents a device, group name, which represents a user-defined group of devices or machines, and then dataset writer name, which represents the actual messages that get published. Further, in the same way that you can use wildcards on MQTT topics to discover more information, OPC UA over MQTT offers topics that you can use wildcards on to discover information about your network. For example, you can subscribe using a wildcard on the status topic to discover all publishers that are publishing data to your MQTT broker. And since the status topic happens to be connected to MQTT's inbuilt last will and testament feature, you would also get reports when a publisher goes offline, among other system-related information. And if you need to find out the schema of all the messages that are being published to the broker in order for you to decide which ones to listen to, you can subscribe using a wildcard on the metadata topic. So, in reference to the recommended MQTT topic tree, status and metadata in this case represent message type. Notice here that these message types provide data about elements in two different levels of the topic tree hierarchy. For example, status provides information about publishers, which is at publisher ID level, while metadata provides information about the schema of all the messages, which is at dataset writer name level. That's essentially how message types work using the recommended topic tree. However, status and metadata are not the only message types that are available for providing system-related information. So let us take a look at the other message types, starting with message types at publisher ID level. In addition to status, which is used to detect publishers as they appear and disappear from the network, there is also application message type, which you can subscribe to get information about the applications that are acting as publishers. There's also an endpoint message type, which you can use to get information about which endpoints in your MQTT network have client-server communication capabilities. You can use this in the event that you need to perform operations that require client-server operations, but of course, you then have to know the client-server connection details of that application. Next, there is the connection message type, which provides you with metadata for all the dataset writers that are published by a particular publisher. This is meant to give you complete descriptions of all datasets produced by a publisher so that you can set up your subscriber ahead of time to receive that information. And finally, we have the nodeset message type, which is a nodeset fragment that provides the subscriber with basic information model context. I'll clarify what we mean by nodeset fragments shortly. Moving on to message types at dataset writer name level. We have the data message type, which provides you with the actual live data in the form of name value pairs. And then the metadata message type, as explained earlier, provides you with the schema that describes the data that is published. And then finally, the source message type provides the subscriber with complete context of where the data is coming from. Simply put, the source message type provides a mapping between the fields that are in the published dataset and the nodes in the OPC UA address space from which these fields originated. And in case the node set goes above the size limit allowed through MQTT brokers, it is sent in fragments. Further, in order to associate the types that are used in the published node set, the subscriber would need more information. And for that, the subscriber would either use a pre-configured companion specification namespace, or it could refer to what is called a UA Cloud Library, which is an online platform that stores OPC UA information models and provides access to them via a REST interface. So, when your subscriber gets the data types from the UA Cloud Library or inbuilt companion specification, it can then use the nodeset fragments published to it to reconstruct the publisher's address space that is being used to populate the fields that are in the published messages. Moving on, as you may be aware, OPC UA client-server model has a feature called methods, whereby an OPC UA client can invoke a method in the OPC UA server that performs a specific task. In OPC UA over MQTT, these are called actions. OPC UA over MQTT actions can be represented in the recommended topic tree as follows, whereby the action group name could be used to represent an object, for example a pump, and then the action name could be used to represent the name of the method or action, for example start pump. So when an OPC UA over MQTT application receives an action topic, it processes it and then returns the response using the same topic that was provided in the request. Okay, so to conclude this section, if you want to start building OPC UA over MQTT applications, you can check out an open source implementation of OPC UA over MQTT supported by the OPC Foundation called the UA IIoT Starter Kit. It's available on GitHub, and you can use the link in the description below to check it out. Okay, so now that you understand the OPC UA PubSub specification and the OPC UA over MQTT implementation, what I would like us to do next is to go through a practical demonstration of publishing OPC UA data over MQTT using Node.js. In this section, I'm going to show you how to publish OPC UA messages over MQTT using Node OPC UA, which is an open source Node.js implementation of an OPC UA server that has the capability to extend its functionality to include OPC UA PubSub. I'm going to be simulating sensor data within the application and publish it to an MQTT broker in the cloud, and then use an MQTT client application to subscribe to the MQTT broker to view this information. So first, let me take you through my Node.js application. So this section here is responsible for importing packages that I've already installed. This here is the Node OPC UA server package, and this one is the OPC UA PubSub extension, and this package here is for types in OPC UA. Now here we're creating an instance of an OPC UA server, and then we initialize the server, and then here we get the namespace for our OPC UA server address space, and then we add an object to our OPC UA server address space called sensor. We give it the browse name my sensor, and then we put it inside our root folder. Next, because we want our sensor object to give us temperature readings, we add a temperature variable as a component of our sensor object. We assign it a browse name, node ID, data type, and a value. And then moving on, this here is the code that generates random numbers and assigns them to our temperature variable so as to simulate our temperature sensor readings. Okay, so at this stage, our OPC UA server is ready, and we've populated its address space with our temperature sensor object. Now we need to add PubSub functionality to our server. So to do that, we get the PubSub configuration details from our user-defined method, which we'll see shortly. And then here we install PubSub on our server. And when that is done, we start our OPC UA server with PubSub functionality. And then next, this here is our PubSub configuration method. And here we also use a user-defined method to create our PubSub connection. And then we also use another method to build up our published dataset. And then we return a PubSub configuration data type. Okay, now let's take a look at our create connection method. Now inside this method, we create an MQTT endpoint, and we create a dataset writer and specify our MQTT topic under transport settings. And then after that, we create a writer group and then create a connection where we specify the transportation mechanism as MQTT with JSON encoding, and put our MQTT endpoint information and then return the connection. And then finally, let's look at our method for creating our published dataset. So here we create a published dataset and specify the fields of our dataset metadata. As you can see, we have created a field called name and assigned sensor temperature to it. Next, we put the node ID that specifies the source of this data in the address space, which is the node ID that we assigned to our temperature variable earlier. Okay, so that's all we need to do here. So our OPC UA PubSub application is now ready to publish OPC UA data over MQTT. Now, before we run this application, let's head over to my browser so I can show you my MQTT broker. Now here I'm on my Azure portal. So this is where I've deployed a HiveMQ MQTT broker cluster on an Azure virtual machine. Now if I go into my virtual machine here, you can see the details of my virtual machine, and this here is the IP address of my MQTT broker. And then here on this page at port 8080 on the same IP address, I've got my HiveMQ broker dashboard. So as you can see, my MQTT broker is ready to receive messages. So let's go ahead and start publishing OPC UA messages over MQTT to this broker. So to do that, I'll go to the directory where my NodeJS application is located. And then I'll run the server.js file. Okay, so our OPC UA PubSub application is up and running, so we should be publishing messages to our MQTT broker. Now what we need to do is to subscribe to the same MQTT broker to see if we are successfully publishing OPC UA messages over MQTT. And for that, I'm using an MQTT client application for testing called MQTT.fx. So if I go into settings here, you can see that I've got the same broker IP address. So I'll go ahead and apply these settings and then go on to connect. Okay, now that we're connected to our MQTT broker, I need to go ahead and subscribe to the same topic that we're publishing our OPC UA messages to. So I'll go to subscribe. Okay, and then click on subscribe. Okay, so as you can see, we are receiving our sensor temperature value. So we've successfully built an OPC UA over MQTT solution. And from here, you can subscribe to this information using some visualization tools to build a dashboard, or you can simply store this information in a database. If you found this video useful, please give it a thumbs up. And in case you aren't already, please do subscribe to the channel. Thanks for watching.